Hello again, everyone. We'll continue with subproblem 3 from tutorial 6. What we need to do is draw the suffix tree of t, the computer version as it is stored. We need to add the offsets in the nodes, the starting index and leaves, and the first character on the edges. So let me remind you, this was the non-compact version of our try tree for text t. This was the compact version, and now, but the human one, and now we need to do the computer one. So we will go here. So what you need to do, what I suggest doing, is first of all, the inner nodes, the red nodes here, you basically need to add on to them, like it says here, the offsets in the nodes. That means that at what point in the text, in which point are we in the text. So, for example, for node 0, for the root node, obviously we are still at the beginning of the text. We haven't checked any letters, so we have label 0. And then, if we add another letter, so we add A. So if we go to this node here, we are at position 1. Come on, let me change it. Yeah. Character 1. After that, if we add BBA, we are then at position 4. So we're done with the inner nodes here. So let's go from the other side. So again, we're at the beginning, position 0, have letter B, therefore this should have value 1. After that, if we add A, we would be position 2. Then we're done, we reached leaf node, let's go back up. So 1, add 2 letters, so this should be 3. And this way we're done with the inner nodes. Now after that, what you probably want to do is fix the leaf nodes. So let me bring you back up. So these were the suffixes that we had. So what you do is you go to each suffix, you say, okay, this suffix $, okay, it's here. So which position is the first letter? It's at position 8. Therefore, change this to 8. Go to the next one, $. Go to $. The first letter is at position 7. Go here. Equal to 7. Then $. That is starts at position 6 or index 6. Here is 6. Yeah, these are basically the indices, starting indices of each suffix. Then we have A, BB, A, $. So it's this one here. It starts at position 3. Change this to 3. Then we are at position, sorry, we have this suffix, which is the longest one we have, I think. Yeah, it's this, the large one. It's at position 0. And BAA $, here starts at position 5. And BABBAA $, here starts at position 2. And BBAA $, here says at position 4. Here BBAB, this one, position 1 or index 1. So we're done with this part that said starting index in leaves. Finally, what we need to do is have only one character in all of the edges. So you see all of the edges here, some of them hold multiple characters. So the only thing I'm going to do is go to those that have multiple ones and delete the last one. Let me check something. Yes, I'm back. So need to delete basically all the characters from our edges apart from the last one. Ta-da! Oh, wait, why is it like this? Did I miss anything? Oh, didn't refresh. Okay, so this way we're done. Sorry, I know maybe these are not so easy to see. Hope they are. This week has been really difficult trying to find an application to use to draw the graphs and so that they can look good and not just use MS Paint. Yeah, so we have finished the third, sorry, these are the solutions. We have finished this third suffix tree, the third subproblem, the suffix tree of T, the computer version 1. And the solutions will basically have the exact same graph. So I'll continue with exercise 4 afterwards. So we're back. What we're gonna do is subproblems 4 and 5 now. So we need to draw, or actually construct the suffix array L0 to n of t. Now this is quite simple. We can do it very fast because of the way we constructed our suffix tree. Since we constructed it, and by using doing it in alphabetical or lexicographical order, so always having $AB and always in that order, what we need to do in order to find it is basically do a Bfs search. So what we're doing is going to start there and going to start searching the tree like this. And I'm going to add each leaf node that I meet to my array. So this is the search I'm going to do. So first I meet 8. After that I meet 7, and 6, and 3, 0, 5, 2, 4, 1. So here we have our suffix array that we needed. Once again, so we do a Bfs search here in order to find it. The only reason that it works is because we created this in a lexicographical order. So this needs to be sorted alphabetically in order for this to work. Next, the problem is to create the inverse suffix array R O to N 0 to N. Sorry, I'm getting tired. So in order to do this, what you do is it's basically the inverse array of L. So in order to find it fast, what you do is, okay, I need to find the value at index 0. So I go to value 0 of my suffix array, which is 0, and I see at what index position it is. It is at 4. So I add it here. And I want to know what value I should put at index 1. So I go to value 1. So the index and the value have to be the same here. I go to value 1 here, and I see that I have index 8. Then I want to find the value at index 2. So I go to the suffix array at value 2, and I see the index. It's 6. Again, value at index 3. So I go to value 3. It's the same, so add 3. Again, value at index 4. So I go to value 4 and I see index 7. And I go to I want to see the value at index 5. So I go to basically value 5, which is in the same position. That's why this is 5 as well. And I want to see the value at index 6. So I go to value 6 and I see that the index is 2. And I want to see the index, the value for index 7. So I go to value 7 and I see 1 as the index. And the value at index 8. So I go to value 8, I see index 0, so I put this as a value. And this is how I construct the suffix array and the inverse suffix array. Give me a minute. Yes, I just check the solutions and it's, sorry, the exact same thing. So we're done for this, and afterwards we will continue with subproblem 5.